Proved by mathematical induction, this formula here. So first up, let's look at n equals 1. The left-hand side will just be, well, we can get rid of the summation sign. It's just going to be 1 over 2 times 1 minus 1. It's just 1. And then 2 times 1 plus 1, that's going to be 3. So we're going to get a third. Meanwhile, the right-hand side is going to be 1 over 2 plus 1, also a third. So this is true. True for n equals 1. Now we're going to assume that it's true for n equals k. Some value of k further on. Let's say that k is a natural number. So under this assumption, that means that the sum from r equals 1 to k of 1 over 2r minus 1, 2r plus 1 is equal to k over 2k plus 1. And we want to prove that's then true for n equals k plus 1. That's how induction process works. We show that the first one works. We show that if n equals k is true, then n equals k plus 1 is true, and that everything comes together because n equals 1 would imply n equals 2, which implies n equals 3, and so on. So let's just write down what we're trying to get. I think that's, in many proof by induction situations, that's what I would advise. So we're trying to show that the sum from r equals 1 to k plus 1 of this is equal to k plus 1 over 2 k plus 1 plus 1, which if I expand it, will give me 2k plus 3. So that's what I'm trying to end up with, then I can kind of write it back as a factorized form, and then we're done. Okay. So we're going to start with the thing that we're trying to get to. So r equals 1, k plus 1. But now all I can use is, well, this essentially. Okay, that is what I know is true according to my assumption anyway. So I can change my summation to being from r equals 1 to just k. And then I can add on this extra term when r is k plus 1. So it'll be 1 over, okay, I'm going to struggle to fit this in. Let me just make a bit more space. One over 2 k plus 1 minus 1 to k plus 1 plus 1. But now I can use my assumption that this thing here is actually equal to k over 2k plus 1. So it's then going to become that k over 2k plus 1 plus, and I'm going to expand and simplify this. I'm going to get in a bracket 2k, then I've got plus 2 minus 1, so that's going to be plus 1. And then 2k plus 2 plus 1, so that's plus 3. Yeah, I've just got to add these algebraic fractions. What I can do is put them over a common denominator. So just times the left-hand one by 2k plus 3 over 2k plus 3. That's going to be our lowest common multiple. Yeah, we're nearly there actually. So that is going to give me, let's just keep a track of what we're trying to get to. trying to show that it can equal this. All right, let's keep going. So it's going to be 2k squared plus 3k plus 1. So we've got a quadratic on top, whereas we don't want that. But you can see that something's got to cancel out if this is going to work. And then on to the next line actually, sorry. Okay, now I know if this is going to work that the 2k plus 1 is going to cancel. So when I factorize it, that's what I'm going to try and get in the top. So then I'll need just a k plus 1. And if we expand that, we see it works. 2k squared plus 2k plus k. That's that bit sorted and that bit plus 1. And now these cancel. And this gives us the result that we want. And we could, if we wanted, just write it back as k plus 1 over 2k plus 1 plus 1. As required. Okay, so start on the left-hand side, used this result here that we've assumed, and we've got the required formula. So hence true, therefore true for n equals k plus 1. I should just say if true for n equals k. And I always write a little conclusion, so I just say n equals 1 true, and n equals k true implies n equals k plus 1 true. By the principle of mathematical induction, summation what do you call it, star. I could write the summation out. Summation star true for all natural numbers. Okay, well done.